And this is what we have discussed from Monday's lecture. Okay, now I want to break down what we have learned before. Now we are going to look on the integrals, double integrals in polar coordinates. So now the idea of the polar coordinates for the double integral is the area that you have, the xy plane. We need to change the xy into the polar coordinates. Okay, so if you want to look at, then if you want to observe the area here in xy plane, or in r theta, we can set the theta from alpha, for example, to beta as our observations, okay, offsets, and then we can set up these equations for limit, and then we have the delta A for this case, similar with what we have done before, but the delta A itself will be different. The area that we will going to observe, we will approach through this equations, the sector equations. Okay. Let me erase this first. So the sector equations, if you look at here, or let me put some pictures here. Okay. Now this will be our sector. So the idea to approach this area is you have a theta from alpha to beta, and also the radius, the difference in radius. Okay, and that will be our area R. Okay, and then if we break down this whole area, the R, if we are making, let's say, in a rectangular figure or similar to rectangle, and make it a bit of pieces like this. Okay, and let's point out the middle point of this rectangle as Ri and theta j. That's the first axis and the second axis. Okay, and so this is the middle point. Okay, the middle point, and every terms, the next terms is Ri. The previous terms are Ri minus 1. Okay, that's it's similar with the pattern you have from before or from previous chapters. Okay, let this Ri. Let's make some definition here. So the middle point, of course, it's half of the R and the previous R. Okay? And then make the theta also equal with the it's J. With the R, it's the same middle point. Okay. Now for the delta A, based on what we have here, let me put here delta A. Let me put here delta A. We can write down this or area will be the R area is the large sector, right? Minus the small sector. Okay. Now we can take the large sector. It's half Ri squared, and then minus half Ri minus 1 squared delta theta. And this will be resulting. This Ri is this Ri, okay? So Ri and Ri minus 1. So we want to approach the the small rectangle. Okay, so this is the delta for, or the area for the small rectangle. So this will be minus, and then delta theta, because the theta will be similar. And by quadratic formula, or by factorizing this, we can have this and also this. Okay. And by our definition for plus and minus, we got the definitions for Ri for the middle point, right? So this will be our Ri, and let the difference between Ri and Ri minus 1 will be the delta R. Okay. This will be delta R. Okay, the difference on R. Okay. Now we have delta A. Okay, and now we are going to look at this delta A and put it on our limit here. Or let me make into a new page so as a conclusions. So or maybe directly writing as a limit to make it more simple. So limit m and n both are going to infinity. And let me write this r cos and also r sine. Okay. And then this will be the result of the delta A. Okay. And we can write this in terms of functions g. Or we can write this as okay. Or in terms of double integral, we can write this, because it's already defined on the limit. The theta from alpha to beta. The r is from a to b from previous picture. And this will be the functions for the polar. And then this will be dr, d theta. Or if you want to write down in terms of f, you can also do that. This is just r cos theta, r sine theta, and then the r d theta. Let me write here is, let's say we have the original double integral, and we can actually convert the integrations if we know the radius, if you know the angle that we want to observe, and we can convert them into this this polar version. Okay. Okay. So this will be true if, okay, the theorem, if f is continuous on a polar rectangle R given by 0, and then alpha to beta for the angle, where the angle itself is from 0 to 2 pi. And then I don't want to write any this equation, so I just make this arrow here. Okay. 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 So let me give you what can we do from here, okay, in an example. For example, you have this kind of double integral, right? If you think and maybe try to evaluate this, probably we can have step-by-step solving from the inside, right? And then you have x squared y, and then you have y cubed divided by 3. But then your boundary is from 0. 0 is easy to be calculated, but here you have square root of 1 minus x squared, which is, if you are going to put in here, you will get into some, unless you want to do it slowly and carefully, and actually you still can probably solve it. But anyway, what I want to show you is, instead of doing that, we can convert this if we think that this is easy to solve by polar. We can convert to polar. First, let's just write what we have here. We have the rectangle R for xy from -1 to 1 for x, and from 0 to this square root of 1 minus x squared, right? So you have this two constraints or two restrictions. And if you want to draw what kind of picture we can solve from here, the picture is actually it's a half circle or half disk. If you want to draw, so this will be from 1, -1, and then this will be y equal, and if you check, it will be true, right? It will be true. So instead of using the xy, we can also exchange the xy to r theta. So of course, the r is 1, right? And the theta is from 0 to, this is theta is 0, to theta to pi. Okay? So you can also convert this. So whenever, in a quick resume, this part here is a giveaway that this is half circle, or maybe something related to circle, because you can also have this negative, right? And this will be a full circle. Okay. And now what we are going to do, let me write the original equation first. This is x squared plus y squared, right? This is dy dx. Now x squared plus y squared is a circle, right? It's r squared, so we can exchange that also. So it's become r squared. And now what we are going to do, This dy dx, if you remember what the formula we have here. Oh, sorry. I think this should be having r here. This should be having r. As in this, if you can see here, it's r. Okay. So we can exchange dy dx into r, dr, d theta. Okay. So we can write the theta first. That is from 0 to pi. Okay. And then write the radius is from 0 to 1. And then this will be, or maybe here is r, dr, d theta. So we will have the r cube, right? We solve through the dr first, and we get r with power of 4 divided by 4 from 0 to 1, and then d theta. And this will be resulting 1 over 4, right? 1 over 4 integral, it will be just a constant, right? Just 1 over 4. And then integration of d theta is just resulting pi. So it will be pi over 4. The result is pi over 4. Okay. And now, aside from conversion, that will be probably help you in any problem that you might encounter. Because it's polar, then you need to also remember some parts on chapter 10, especially about some of the polar equations, like maybe the cardioid, okay, or having loop, or having the lemniscate, or maybe the rows, right? The rows and some, I think this is most common polar that you might encounter, especially the loop or cardioid. And yeah, the cardioid is maybe you can check in at the exercise, or later I will upload the exercise. Okay, let me give you another example, and then we can let me check. Okay. Okay. Another example. Now you have double integral r sine theta and dA. Okay. Let me write the questions, where r is region outside circle r equal to, and inside r equal 2 plus 2 cos theta in first quadrant. Right? Okay, now we have two polars. R is equal to, it's a circle, and 2 plus 2 cosine theta. That's the cardioid. I hope you still remember that. First, in double integral, my suggestions, as in the previous lecture, sometimes you need to check the area, how it looks like. Okay, at least some rough sketch. Okay. That will be the circle. And then you have because it's 2 plus 2, so it should be, this should be 2, should be 2, so it should be intersect here, right? And then you have, this is 2, so this should be 4 here. Okay. Yeah, more or less, and that's the cardioid. Outside of the circle, but inside of the cardioid. So it should be inside cardioid, but outside of the circle. So probably here, but it's only on the first quadrant. So that's the first quadrant. Okay, from 0. So first quadrant is 0 to pi over 2. Okay, the first quadrant. Now we have the theta here. And if you look at the polar, as you remember how to take the, which one is the top boundary, which one is the lower. If you look here, then you will get that the polar is having this kind of structures, right? You have a difference in angle, right? So the blue one is the top, and the what color is this? Or maybe just red. The red one is the lower boundary, right? So we can write this r, or in terms of the questions, this is sine theta, and let's just write r dr d theta. So d theta is, our theta is from 0 to pi over 2, and the r is from 2, right, to the cardio 2 plus 2 cosine theta. Okay, now we can integrate r first with respect to dr, right? That should be not a problem. So sine theta, and then r squared over 2. And we plug in 2, and 2 plus 2 cosine theta, and d theta. Okay. Okay, let's solve this. Sine theta, and then over 2, and r squared is 2 plus 2 cosine theta squared minus 4, and then d theta. And we try to solve, try to expand this, and minus 4, and then we get, let me write half outside. So we still have sine theta, and then the inside will be 8 cos theta minus plus 4 cos squared theta, and then d theta. And if you look at the results here, you will see that okay, maybe the half I will put inside, and to simplify the number here, so maybe it will be 4, or maybe combine to just to make it clear. Okay, now what you are going to do from here? I think we can, or maybe factorize 2. Right? Okay, if you look here, it's precisely this is sine 2 theta, in which we can easily do integral, right? And what we have here? If you want, we can separate this. Like first we have this integration, and second we have this integrations. For these integrations, we can have a substitution. So I think it's easy just to use the substitution method, and you can have this is, and we can substitute the d theta and make it negative sine theta du, right? So you will have u squared right here from here, and you can simply take integrations and change back to the u. So we have 1/3 cos theta. Okay, and then I think it's easy to just plug in the theta. It's also easy to plug into this minus 2 at, sorry, 3. Wait. And this just make integrations. And then all will be multiplied by 2. Okay, so this will be there. Okay, and you can solve this and find the answer. Okay. Okay. Yeah, because in polar, most of the cases you will get sine and cosine. What I'm suggesting is for polar, to solve it, first you need to remember some of the double angle formula, okay? And then maybe using some substitution method to solve the integrations. Yeah, I think just this two, I think that's enough to check and to solve. Okay. I have some other example, but I think I'll skip it. We have 15.4, right? This 15.4. So I will end the 15.3 here. But later I can maybe review, maybe next week for some example if we still have time. 15.4 is actually applications of double integral, but that is most likely about density, mass. I will skip that. Okay, so I will move to the new sections. 15.4. We will skip. And we can go directly to the surface area, 15.5. Because some part of 15.4, I believe you have learned more or less on physics. I will skip that, so it won't be on any exam. So we just skip it. Okay, so surface area. Okay, let me put some. Okay, let me draw some random surface there. Okay. And then on some part here, probably here, let's take same or similar method to what we have done before, mapping all this into the XY plane. Okay. And take this another rectangle here as the R. Okay. And maybe this is the surface of Z. It's functions of two variables. And the area, if I take this to, this is Y, so this will be the delta Y. This should be delta X, right? So we have the delta A here. And this surface here, okay. Let's say this is the point. So this is point IJ. And the red color here is actually the let's say the delta of T. Okay, T is the tangent, the tangent plane, if you remember. And the below here, the blue here is the surface itself. So the surface. So delta means the part that are already cut into pieces. That's really, really small. Okay. Now, based on the graphs here, we can write down the area as in limit, it will be and this will be the delta of the tangent. Now, to see more clearly about this tangent, we need to make another graphs. So let's observe this into a bigger graphs. Let me put here. So this will be the this will be the tangent plane. Okay, I'm making it bigger, and it's going here, and let's map to our XY. Okay, I hope you got it here. So this will be the delta T. This will be all this will be the delta Y. Okay, and this will be the this will be the delta X. Okay. Okay. And then from the point P, from this P here, let me make P here. We then have our factor from P. Okay, here. So we have this factor. Let's say this factor is B, and this factor is A. So let A and B be the factor that start from P, okay, and lie along the plane or the parallelogram, okay, the parallelogram with the area of delta t. Okay. And the parallelogram, if you remember the area, is actually A cross B. Okay. In chapter 12, we have learned about this, right? And then remember on chapter 14 from previous chapters that fx of the xy and f or partial y on the some coordinates, these are, we call it the slope, right? It's called slope of tangent line. Through point P in direction of A and B, right? Now we can set up our vector A as delta x I plus the partial x and delta x k. Okay, and B is delta y plus partial y and then cross these two. Sorry. Oh wait, should be J. Yeah. Yeah, B is should be J. Okay. So this should be 0, delta y, and partial y. Okay. And solve this, we get negative partial x. And let the delta x, delta y, all will become delta A. And we can factorize the delta A outside. And now we have the delta t, or the tangent plane, is the magnitude of the A cross B. So we will have square root of the previous equation. So this will be negative or positive, will be the same because we was going to square it, right? And this is plus squared, and then plus 1 squared and delta A. Okay. An equation from here. I need to few minutes. Okay. Okay, any questions? So we have now this is the area, okay, area of parallelogram or the tangent plane, as you see from what we have done previously. And then from here, we can have our area or surface area. Let me write the surface area like that. It's a limit Sm and n going to infinity. And then the conclusion is we have partial x and we have the partial y. And then plus 1. And then delta A. And then I will conclude this into the definition. So the area of the surface with equation z, and all the points are based on its set of D or at its domain, where partial x and partial y both are continuous. Then the area will be the area so we write all the partial x plus, oh sorry, this should be partial y and this will be dA. So again, it can be dx dy or dy dx. Okay. Now I'm giving you some example here. First is find surface area of the part of surface C that lies above triangular region with vertices okay, that's the first question, so you can try to check. Okay. Okay. Start from the region first. We can draw. This is 0, 0. Let's say this is 1, 0, and this will be 1, 1 here. So we will have a triangle, right? Triangle. Okay, now how to make the region as in the as your boundary. Of course, if you see the point, right, this will be 1, this also 1, right? So y is from 0 to 1 and x is also from 0 to 1. But that will not conclude what we are looking for. What we need also is this line here. And this line is actually y equal x, right? So we need to include these equations, y equal x. So you can use in terms of x or in terms of y. Then you will have a set of double integrations. Let's say it's 0 to 1. Okay. I will write the inside integration from 0 to y or x. That's it actually depends on you. The later cases, it can be dx dy or dy dx. Should be similar results. Okay. So I will write this. This is the area will be maybe let's write here for the z. So z is x squared plus 2y. Let's make a partial x is 2x. A partial y it's 2. So I can directly input all this informations inside here. So this will be 4x squared plus 4 and then plus 1. So it's plus 5. Okay. And I will write this will be dy and dx. Because this is y equal x, right? Okay. Okay. Now we can solve this. Remember, okay, some notes here. When you find if the integration's difficult, try to reverse to dx dy. But I think this should be not too difficult. Okay. So integrate to y. So you plug in y. So y and then square root of 4x squared plus 5. And this should be from 0 to x and then dx. So you can exchange y to x. And then dx. And I think this should be easy, right? If you are using u sub and take the whole thing here for x squared plus 5 and differentiate, it's becoming 8x dx. This is u du, and you get dx is 1 over 8x du, and you will get at least like 1 over 8 something from here. Okay, and then based on that, you can have this is squared of u du, right? So solve this first, and then convert back to x. and then later integrate to replacing the 0 and 1 for the x. Okay, and then we'll get the results. Okay, please all the results and try by yourself so you can have more. You can get used to all these integrals, and it can be as your review for at least the substitution method, and also previously the polar. Try by yourself. Okay, I'm giving you another example. Find surface area of the portion of Z. This will be the surface, the surface that we want to observe, that is below Z equal 9. So you have a plane that is cutting on Z equal 9. Okay, first, if you want to draw, I think the Z is not too difficult to draw if you remember the quadratic surface on chapter 12. Right? So this will be parabola, Z equal x squared. Z equal y squared is also parabola. X squared plus y squared, if it's equal to some constant, it's the circle, right? So we can have a paraboloid with a circle as its area, or like okay. Okay, let's make that as our paraboloid, and suppose that this is 9. Okay, so this will be a plane. Okay, up there, but I will just imagine a plane up above the paraboloid. So we need to check all this surface part here. Okay, so the parabola is actually going through all the points, but we are limiting on Z equal 9. Okay, so this is Z equals x squared plus y squared. Now how to solve this? Probably we can try to find the partial x is 2x, partial y is 2y, and probably we can take some let's make this r. Okay, so this is r. So if you project the parabola into the xy plane, it will be a circle equations, right? So let's write the equations first. This will be 4x squared plus 4y squared plus 1. And let's say it's dA. And if you are going to try to plug in the boundary from this circle here, you can check from y or x. I will for this one I will try from x. So this will be x, and this will be the y, the inside. So it will be this full circle. So this is y equal, okay? And put in all the information here. And it will be dy dx. Okay, as in previous example, we can also convert this. Let's convert to polar. So every time you see any circle equations or anything that related to circle, you can directly convert to polar. And now, when we are looking at polar here, imagine this is being a full circle. So you have a full circle like that. Of course, if you want to apply to all area here, your theta is from 0 to 2 pi, right? And what about the radius? The radius is to 3, right? Because you have 9 as your maximum radius, right? Okay. So yeah, oh yeah, I forgot to explain. This is actually from the circle. Okay, I forgot to explain. Okay, but I hope you understand that. And let's convert to polar. This 4x squared plus 4y squared become 4r squared. We still have the square root, and then plus 1, and then r, dr, d theta. Okay, and now we have 0 to 2 pi for theta and 0 to 3. And I think it's much more easier to solve. And how we solve this is basically the same. We can use u sub because it has r squared and it's just r, and we can cancel this r later on our u substitutions. So we can use sub this into u. So we can have this dr du, and dr is 1 over 8r du. So we can basically cancel this to this, and we have 1 over 8 square root of u du. We can solve this first, and actually you can also write this as if you want, okay, because you know that the r and the theta is separate equations from here. So you can write this as d theta and write this as this polar. Okay. So if you want, you can calculate this, integrate, and then you can check the results later. Okay. Okay, let me give you an example, but thing we can have several examples. Maybe here another example. Okay, if you read these questions, the region R means this is the rectangle. Okay, rectangle. Rectangle from 0, 1 and 0, 4. This is X and Y. Okay. Okay. I think you can try to write this down on your exercise. But before we are finishing our lecture today, I would like to let you know that I think first is next Monday. It's June 14th. Okay. It was supposed to be holiday, right? Do you want to have a course on that day, or because if you don't want, but I want to request additional course to replace the Monday, or just having Monday morning class as usual, and then just that. What do you think? Maybe I will ask again later on the Google Classroom. Okay, so I hope June 14, although it's holiday, I hope we can still have one lecture that day. Or if you don't want, we can replace in another day. But anyway, since we cannot go anywhere, so that's why I want to propose. Although this holiday, let's have a course here. Okay, what do you think? You can reply me through chat box. Do you want to have course on Monday, or we will have a course on Saturday? It can be this Saturday or next Saturday. It's okay, right? Because usually it's a holiday for the Dragon Boat Festival, but since it's the level 3 pandemics, right? So we cannot go anywhere, and I believe, yeah, right. You don't really have anything to do because you are at your home and you can go anywhere. Right? Yeah, unless you can go anywhere, and we can. Oh yeah, Shelly, you raise your hand. Do you have something to say, or ask some questions? Okay, okay. I think it's okay, right, for Monday. So I will post again since Monday is holiday. I will post some announcement that we will have a course on Monday, and I hope we can finish on time. And I will also asking a survey later on the Google Classroom and also the Moodle about the schedule for your final. And if you have other schedule, like other course schedule, and it's already fixed, please let me know, and I can think on what time we can have our final. Okay, if you check your Google Classroom, I have scheduled the quiz for today. You can check that out. The time is actually only 25 minutes, but I can give you 30 minutes. So please check the Google Classroom. Our new announcement. There is a link to quiz, chapter 14. Yeah, you can start from now. It's actually 25 minutes until 11:55, but that's okay if you want to take your time until 12. Okay, so 12 is the limit. So you can check and you can start anyway. You can look at your notes, open your book if you have. Yeah. And I don't really, for the paper calculation, you don't really need to prepare it for now. Okay. So you can just start and write the numbers based on each questions. I will stop the recording.